Okay, so thus far in the course, we've talked about electricity and electric fields, um, going from the basic idea of a charge and Coulomb's law, how charges are attracted or repulsed. We then moved into electric current and how circuits work, and then we moved into magnetism. So now we're going to finish off this sort of flow of ideas and actually discuss electromagnetic induction. So we're actually going to link all this together. We're going to talk about how magnets influence current influences magnets, magnetic fields. So in this module, we're sort of going to bring everything together. So um, when we start talking about electromagnetic induction, um, a key person that will come up would be my personal favorite. One of my personal favorite scientists is Michael Faraday. He actually only had a basic school education and was largely self-educated. Um, he started work as a child pretty much as a bookbinder, but was a very curious person and eventually started working for a quite famous scientist when he was younger. But in 1831, he actually made a very interesting discovery when he actually moved a magnet into loops of wire. So instead of just getting like a compass close to wire like we talked about previously, this is more targeted and more intentional. He had a current loop and was actually I'll take that back. He had a loop of wire with no current in it, um, and actually discovered that putting a magnet through this loop would actually cause a current to happen. So the current was induced. This electromagnetic induction, which was also discovered by Joseph Henry around the same time, was essentially a new way to produce current. Uh, Normally, what they were doing in England at this time was just using batteries. I believe they were acid batteries at the time. And for the longest time, that's how they assumed that you would get current through a wire to, light a battery or something, or light a light like a lamp, just using batteries. So this is a interesting discovery that without using a battery, you can still put in some sort of mechanical energy to get a current out. Um, Faraday did do a lot of interesting work. He contributed to increasing the safety of coal mines, invented new ways of operating lighthouses, and even worked on ways to control pollution. Um, he was welcomed into several prestigious societies when he was older, and actually was quite famous. Made several other scientists jealous. But again, his math skills were not that great. Like he became famous with just very basic algebra and virtually no trigonometry skills, which means he approached a lot of his science with pictures and drawings and illustrations. And he actually visualized electric and magnetic effects and with these lines of forces, he called them, and that's what we actually use as field lines today. So you can imagine the lines we've been drawing with magnets, south, and then on the charges, we have an electron. All these field lines we've been using is actually sort of developed from Faraday's work. He actually gave a lecture at the Royal Institution in London, I believe one Christmas, and then sort of set the tradition of the annual Christmas Eve lectures, the Christmas Eve lecture series at the Royal Institution in London. And actually, I was in London not too long ago and got a chance to go myself. So I had to share these pictures. This auditorium was actually the same room that Michael Faraday and a lot of other famous scientists actually gave very influential lectures, actually just to the public. There's if you ever go to London, I highly encourage you to go see a lecture here. It's a very old building, it's a very old institution, and you can sit in the same room as some of the greatest scientists that's ever lived, where they've given lectures. Just for funsies, you can zoom in and maybe not in this particular picture, but the one on my phone, this lady here is giving me a really irritated look for some reason. All right, so enough about Faraday and my adventures in London. Let's actually jump into electromagnetic induction. So, electric current can be produced in a wire just by moving a magnet in or out of loops. So you don't need a battery or no other voltage source. This can just happen. So all it takes is just sort of, if you just go in and then stop, the current goes away. If you pull it back out and stop, the current will go away when the stop happens. But you can actually get a current or a voltage. I guess I should say current and a voltage, just by moving a magnet through a loop of wire. And what drives this is the change in motion. So just putting a magnet in there doesn't do it. The magnet has to be moving. Magnet must be moving. So this whole phenomenon of inducing a voltage by charge or by changing the magnetic field in loops of wire is called magnetic induction. And a lot of times you'll see that abbreviated as EMI. The voltage is induced by this relative motion between a wire and a magnetic field, whether the magnetic field of the magnet moves or the wire moves. So you're going to get this effect either way, if you move the magnet or the magnetic field, or whether you're moving the wire and the magnet's actually sitting still. As long as you have the motion or the relative motion of one of these things, you're good to go. You can imagine if you increase the number of loops in a wire, you actually get more of a voltage. So the number of loops, if you increase those, more voltage comes out. You can see over here, we stick this magnet in just a couple of loops. You get just a little bit of a change. If you increase the number of loops, you'll notice that the needle goes over a little bit more. And then if you add even more loops still and input the magnet again and move it around, that's sort of when you reach the maximum. Obviously, you can just keep making more and more loops if you want to. It kind of seems that we get something from nothing just if you increase the number of loops, but that's actually not quite true. So this is, if you assume that your coil is connected to some sort of resistor or energy dissipating device. So if we were to have a resistor in here, so it turns out you're going to lose some energy through the resistor. That sort of gets rid of the whole idea of, oh, it's free energy. Also, when you try to push a magnet through, the more coils you have, it actually gets more difficult. You can actually have more resistance on that magnet. So you still have to sort of add additional energy to fight that resistance while you also have to add energy to move the magnet. And that's just because that induced voltage makes a current, which also makes an electromagnet, which repels the magnet in our hand. So not only do you have the magnet itself, you also get a counteracting magnet in the coils of wire. Okay, so the current also has a magnetic field. Because you'll remember last time when we had a coil of wire and we were talking about the magnetic field, how it sort of went like this. See, you've got two magnetic fields in there that are interacting with each other. So there's the problem. Because you also have the magnetic field of the magnet itself going into the coil. So it is more difficult to push a magnet into a coil that has more loops because the magnetic field of each loop resists the motion of the magnet. So that's something you have to overcome. Of course, you could try and push this in slowly, but actually a slow motion, remember, this is dependent on motion. A slow motion actually doesn't give you any voltage or hardly any voltage at all, but a quick motion, that'll actually increase your voltage. So the voltage is somewhat dependent on the speed of the magnet. I'm just going to say M for magnet. So the faster the magnet's moving in there, the larger the voltage you can get. So let's think about this one quick question. There's no math, so we'll just go ahead and jump right to the answer. Is electromagnetic induction EMI an energy source? And the answer is no. EMI is not a source of energy because it's not sitting there for free. It's just a method of transforming mechanical energy into electrical energy. So we have to do work. This is nothing but an energy transfer. Now, it turns out that this electromagnetic induction is summarized by Faraday's law. And Faraday's law is kind of wordy, so we'll go through the text of it and then we'll look at essentially the equation. The Faraday's law states the induced voltage in a coil is proportional to the product of its number of loops, the cross-sectional area of each loop, and the rate at which the magnetic field changes within those loops. That is a lot of words, so let's look at it mathematically. So the voltage induced is proportional to the number of loops or number of coils. Okay, so that's N. The area of the coil, so the cross-sectional area. So these would have a big cross-sectional area, these coils would, whereas these coils would have a little cross-sectional area. Basically just the size of the tunnel that the magnet's going in. Whatever that area is the A in this equation. B is the change in the magnetic field, and delta T is just how long it takes for that change to happen. This is something we've already talked about. This is a rate. So that's just almost like a velocity. It's just how long it takes something to happen. That's why only the motion of a magnet in a coil will cause an induced voltage. If you just put in a magnet in a coil and leave it there, that doesn't do anything. You'll have a voltage when you put the magnet in, but as soon as you stop, the voltage goes away. That's because if your magnet is not moving, so no motion, if your magnet's not moving, that means you have no rate. So your change in your magnet over time, that's just zero. There's no rate. So this equation up here would be zero. Well, technically it's not an equation since there's no equal sign. So this proportionality is zero. Something else to remember though is the amount of current produced by electromagnetic induction depends not only on the induced voltage, but also the resistance of the coil and the circuit. So Faraday's law, you have to keep in mind, like if you wanted to figure out how much current's going to be going through the circuit, you still have to come up with a resistance for the circuit and everything. So this means there's pretty much three ways in which voltage can be induced in a loop of wire. So you can move the loop near a magnet, or you can move a magnet near a loop. We've already talked about that. Essentially, one of the two things needs to be moving, or you can actually change the current in a nearby loop. So if we have one loop here and one loop here, and we'll talk about this next time. But essentially, if you change the current, so delta I for a change in current in one of these, will actually, let's use a different color, it'll actually change the current in another. So there's 3 different ways we can actually induce a current here. And all of these essentially they reflect Faraday's law, which is a changing magnetic field in a loop will produce a current. All right, let's take a look at another, not really a math example, so we'll just jump straight to the answer. This is more for discussion. So we have a simple security system consists of a miniature electric circuit at the top of a door and a nearby small magnet fastened to the door frame. How is an electric current generated when the door opens or closes? Okay, so it sounds like we have a door and we have, let's see, a magnet up here, and then a little mini electric circuit on the door. Okay, so there's a coil of wire. So you can see that what's going on is essentially we have a magnetic field from the magnet, and then when the door is closed, nothing's happening. We have closed door. Everything's static, nothing's changing. We have no rate, right? So there's no induced magnetic field, there's no current. But when the door opens, that means the magnetic field is starting to change. It no longer equals 0. And that's actually how we get that induced current. So the magnetic field of the magnet extends to the coil in the system, and then the field in the coil changes when the door moves. So field changes when the door moves. We need that motion, and that'll actually set off the security alarm. All right. So hopefully this GIF is working here. But essentially, when you plunge a bar magnet repeatedly into and out of a coil of wire, the direction of the induced voltage alternates. And you can see that here, we're going from a positive voltage to a negative voltage. And it's constantly alternating. That's just because it depends on the direction of the magnet. So as the magnetic field strength inside the coil is increased, the induced voltage is directed one way, and then when the field decreases, so when you take the magnet back out, the voltage is induced in the opposite direction. So the frequency, so how fast this happens, frequency of the alternating voltage is equal to the frequency of the oscillating magnet. Okay, so if you want, you can imagine if you wanted like 60 hertz alternating current, which is what's coming out of your wall outlet at home, you'd have to move that magnet back and forth essentially 60 times a second. So it's more practical to induce a voltage by moving a coil instead of by moving a magnet. Obviously, to get a large magnet to do this, it's going to be really heavy. So it kind of makes sense you want to move the small coil instead of having to move a magnet back and forth really fast. So the whole idea is you can essentially do this just by rotating the coil inside of a magnetic field, just like this. And this arrangement is essentially a generator. The construction of a generator is the same thing as constructing an electric motor. It's just the input is reversed. You're literally running an electric motor backwards, but they're the same thing. It's just that in a generator, mechanical energy is the input and electrical energy is the output. So it's just backwards. You can see here we've got don't know which one's which, but I'm going to assume this is North and South Pole. So we have a magnetic field in here. looks like we just have one coil, so N would equal 1 here. And all you're doing is you're taking this square and just flipping it through kind of like a rotisserie chicken inside this magnetic field, and that's actually going to generate current in that wire. Of course, you'll need some sort of mechanical input, because remember, this isn't free energy. We have to do work to make this happen. So we're putting in work, but we're putting in mechanical work, and we're getting electrical energy out. All right. So when a wire in a magnetic field experiences a force due to current in the wire, we have the motor effect. Okay, this is literally the exact opposite of the generator. Okay, so the wire, let's see. Yes, when a wire in the magnetic field experiences a force due to current, that's the motor effect. But then the opposite way, when a wire is pushed, so when we're moving the wire in a static magnetic field, that's generator. But when the wire gets moved by a current inside, that's the motor effect. Okay. And we can think about these two things and differentiate them down here in these two figures. All right. So if we look at the first one, we know that we have a magnetic field. So we're going north to south. Okay. And we know we have moving charges. So we know we have some sort of velocity, right? And remember what we said about the force from a magnetic field? It always points perpendicular to both the magnetic field and the current. Um, let's see. QBB. You should remember that from last time in the last module. We have this velocity of current, we have a magnetic field, which is B, then we have the charges that's moving, and always the magnetic force points perpendicular to both. So if we have one pointing essentially left to right, then we have one pointing front and back, then that means the magnetic force must point up and down. And this is the motor effect, okay? Because the wire is moving due to current. Oops, that should be an O. I'm going to try and erase this, but we all know my eraser only works sometimes. There we go. Okay, so motor effect. So this is when we put in electrical energy and we get out mechanical energy. So the magnetic force is trying to push the wire up. Now, if we look at it from the other side, we don't have moving charges this way. So we have no flow of electrons. There's electrons in there, but they're not flowing down the wire. Now, when we actually push this wire into the magnet, those electrons are moving. They're just moving down through the magnetic field. They're not moving in the wire side to side. They're moving down. So we do have a velocity. We have moving charges going down. We do have, this is in a big horseshoe magnet, so we know we have a magnetic field pointing this way. So that's going to be north-south. So we have everything in our recipe for a magnetic force. We have charges down. So charges down, we have magnetic field side to side, which means our magnetic force is going to be in the front-back direction. So check this out. Our magnetic force is along the wire. And since we have a magnetic force along the wire, that's actually going to cause a current. It's going to push everything through the wire. So this causes a current. Okay. Now, obviously, if we wanted to turn this into like a engine or not an engine, a motor of some sort, or if we wanted to do this in a generator, we don't want to have to like shake a wire back and forth the whole time. So let's talk about the electromagnetic induction cycle. If we put a coil on something that spins, like brushes, so it can spin essentially indefinitely, let's look at what that's going to look like. Um, So when this loop of wire is rotated in the magnetic field, there is a change in the number of field lines within the loop. So when the plane of the loop is perpendicular to the field lines, so here's my plane of the loop here. Okay, so you can think about it like holding up a pizza box perpendicular to the magnetic field lines. This is when we have the maximum number of lines in here. So it looks like we have like what, 1, 2, 3, 4, 5, 6, 7, 8 field lines in there. Obviously, there's infinitely many, but for the demonstration purposes here, we just have these 8 field lines. Now, as the loop rotates, fewer lines are enclosed. So we start making that little area smaller. We make the window smaller. You can imagine a spot in here where the coil is turned like 45 degrees, which means we start losing some field lines. So maybe this one can't make it through anymore. Maybe this one can't make it through anymore. So then that's going to start reducing the number of field lines as it rotates. When it gets to flat, when the plane of the coil is parallel to the magnetic field, there's 0 field lines in there. None of those lines are going through that coil at all. So we get 0 field lines. We can rotate again. We're back to a maximum. Rotate again. Back to a minimum of 0. Rotate again. So we're constantly changing the magnetic field in this coil over time. That can equal 0, which means we're inducing a current in here. Now, it turns out the greatest change in the magnetic field, so when this is at its maximum, happens when the number of enclosed field lines goes to 0. And you can see that here. So if we want to plot voltage, we see that while this thing is turning and it's sort of upright, yeah, we have a voltage, but it turns out the math says that, and it works out this way. When you swing through this 0 part, remember it's got to be in motion to make this happen, but it turns out when you swing through the 0 parts, that's when you get your maximum positive and negative voltages. So here's our, I guess I'll say our minimum and maximum. Usually when I say maximum, I just mean like the largest value, whether it's positive or negative, but that's a poor choice of words. So we'll say, here's when you get the min and max voltage, is when you're when your plane is parallel with magnetic fields. So again, we sort of get like this transition here where we're going back to positive, negative. Here's where our maximum voltage. And that again is when it's flat, just because that's how the math works out. If you have taken calculus and you understand a derivative, when you look at the math of Faraday's law, you get a minimum and a maximum actually at angle 0. All right, we'll take a look at not really a problem or an example problem, but more of just a statement. So when a wire loop is made to rotate in the magnetic field, voltage in the loop is induced, right? We've been talking about that. So why? Is it because the wire is moved perpendicular to the magnetic field lines? Or is it because the magnetic field intensity enclosed by the loop changes as the loop rotates? Well, it turns out that this is essentially the same explanation. So if the wire is moved perpendicular to the magnetic field lines, that pretty much causes the intensity enclosed to change and vice versa. So really, both of these statements are explanations as to why this works the way it does. All right, I'm going to stop here. That's our introduction to electromagnetic induction. The next thing that we'll hit is essentially power production and transformers. I think the next lecture in this module will be kind of short, hopefully. And then one more after that, sort of looking at applications of electromagnetic induction. And then that'll pretty much have us finished for electromagnetic induction. We'll move on to something else. So in the meantime, if you have any questions, please reach out and let me know.